I know you have a very different backgrounds from each other, so I hope you'll enjoy the seminar. It's going to be focused on fundamental science and fundamental chemistry, but if you have any questions, please feel free to stop me at any time. Before starting my seminar, I was asked to tell you a little bit about myself. So I made a very personal slides started to just tell you more about me. I'm originally from Italy, and I'm a first-generation college student. Both my parents, and actually this is the first time I ever told my story. So both my parents were born after the Second World War in a situation in which Italy was, coming out of the war. So it was a very people were very poor at the time. They didn't have the chance to go to school. They got married, I think, in the 60s. Had my sister first, and then after several years, they had me. Everything they did in their life was just trying to get me and my sister to study. And that's how they first, this is where I was born, in Wale, which is a medieval town in Italy. And I did my medium and high school around there. And the reason why I tell you this is because, of course, my parents wanted me to study, but they couldn't provide much mentoring themselves. So I had to count on professors that I found along the ways. And my medium high and my high school professors were really the one that told me more or less, okay, I think you're good in this subject. I think you're good in that other subject. Here is what you should do next. So next I went to the University of Padua. That is one of the most ancient in Italy and around the world. It was founded 800 years ago, 1222 exactly. And there I got a Master of Science in Pharmaceutical Chemistry. So in Italy, before you can access a PhD course, you need a Master of Science. The reason why I did a Master of Science in Pharmaceutical Chemistry was because I was hitting two goals: make my parents happy that I could study and have a job immediately after getting a master's, but also have something versatile that I liked. I always liked chemistry, I always liked math and physics. And so that master specifically gave me the chance of learning all those things. So then my dad found an article on a newspaper that was talking about the International School for Advanced Studies, which is a PhD only school that is in Trieste. Trieste is at the border with Slovenia. It's a very international place with many institutions from the United Nations that are doing research. So there is the International Center for Theoretical Physics. There is a Center for Biology. And this school is really focused on a very high ratio or very low ratio between professors and students. So there were very many professors, very little students, and I was really nurtured in an international environment with very high focus on our preparation. And there I got my PhD in physics. After that, my PhD advisor, I was lucky, was retiring from Princeton and went back to Italy, and I was one of his students there. And I don't want to give a naive impression of me, but I want to describe the environment I was in. The first time I got connected to the internet, I was 24. I'm 39 now. So it was not very many years ago. And I'm sure it's very different than the experience that you had. So when I first met my PhD advisor, he's like, I'm a professor at Princeton. I'm like, okay. Like, so what? I didn't even know what Princeton was. And so I had part of that knowledge that, I learned along the way, and I'm here now. So I think it's totally possible and everybody can make it actually. But then he talked to me, and he actually had me come to the US several times during my PhD. So I wanted to have an experience and doing research in the US to try to understand how things were working in different countries. So I came from Italy to here, specifically in California. I went to UC Santa Barbara, beautiful campus. probably even better than I am now. I cannot complain about where I'm now, but UC Santa Barbara does have a place in my heart. I did materials there. They have a very good materials department. Then I moved to UC Berkeley in the chemistry department. I was there for about a year. And I already applied when I became a postdoc at UC Berkeley for the position that I have now at the Lawrenceburg National Lab. I will tell you way more about what I'm doing later, but the reason why I wanted to be at Lawrenceburg National Lab is because I love team science. I love to work with other people. I want to have the expertise and the knowledge from other people feeding into my research. I really take energy from that, and that's why I applied there. So a little bit more now about the research that I've done along the way. As I told you, I have a master in pharmaceutical chemistry. And when I first met my PhD advisor, I told him I wanted to work on drug delivery, partly because that was my background really, but also because I wanted to contribute on societal challenges. And for me, at that time, contributing in pharmaceutical chemistry and trying to make sure that the drug goes exactly where we want it to go was important. So I did my PhD thesis on gene delivery and tissue repairing specifically. I worked a lot with carbon nanotubes, with salt. And what this PhD really gave me was the tools to synthesize materials, modify them, and really come up with creative ways to insert the functionalities that you want on a material. I also did a lot of characterization along the way. And towards the end of my PhD, I used some of the materials that I was making for gene delivery just because they were positively charged. And so they had these dendrons attached on the surface of the carbon nanotube. So those dendrons that can bind genes can also bind catalysts that are negatively charged. So I just use exactly the same scaffold that moved from nanomedicine to catalysis. I learned skills that are from electrochemistry. I learned how to test this catalyst. And this back at the time was one of the most efficient catalysts for water oxidation. And that's how I got into the field of catalysis, renewable energy. I moved away from nanomedicine also because of funding availability at the time. I still think that someday, maybe I'll get back into some research that is about nanomedicine, but I'm perfectly happy now to work in the field I am because I'm feel that I'm contributing to, I guess, societal challenges. That's really what I'm passionate about. And at Santa Barbara, I worked a lot on both organic and inorganic materials. So I expanded my knowledge in a field that I didn't have before. And I learned how to make organic conducting polymers. I learned how to work with inorganic materials that are also light absorbers. So just to summarize, during my PhD and my postdoc, I developed this background around chemistry, physics, material science, biology is less applicable to what I do now, but I still have it. And I am really focused on synthesis and characterization. And I apply this knowledge to a field that is of high interest to me, that is artificial photosynthesis. So I told you earlier, I wanted to join Berkeley Labs because of the team science mission that Berkeley Labs and a lot of the national labs have. What's important here is that back at the time, and still now, there is the hub concept. You might be familiar with this. The Department of Energy has several hubs, energy hubs. And the one that I'm involved with is the solar fuel hub. Before, the project was called Joint Center for Artificial Photosynthesis. Now there are two projects, the Liquid Satellite Alliance, which I'm part of, and CHASE, which is Center for Hybrid Approaches. The goal of these projects is to make a device that can make fuel. So now I'm going to show you a device that makes hydrogen. And this was a device that we realized back in 2015, published in 2017. We actually recently got an R&D 100 award for this device. And it's a video, I'll switch it on, you'll see light going off. And it's basically an equivalent of a solar cell, but as a catalyst on the surface, and that allows you to make hydrogen. So now light goes off, and you see bubbles, and these bubbles are hydrogen. So this is the idea that I'm working on, trying to make efficient device that can make hydrogen, but also utilizing similar principle to make fuels. At LGNL, I work a lot on the interfaces between all the materials components that are in that device. And I also look at the exact catalytic interface between the catalyst and the electrolyte. So I try to make modified microenvironments that are improving the activity and the selectivity of the catalytic reactions. Again, this is like the part, the personal part of my talk. So this is the building where I worked. It's a picture that I took. Very nice sunsets from there. This is the dome of the advanced light source. This is me in the lab with one team of researchers that I work with. And here, this is an instrument that I developed there, an atomic force microscope. And this is my group pre-pandemic. And then my hobbies, I like a lot to travel. I travel as much as I can now with the pandemic in between. It was difficult, but I'm looking forward to start that again. I like eating a lot. As a good Italian, I like cooking and spending time with food and friends. And one of my passions is actually the Cirque du Soleil. So they closed during the pandemic, but now they reopen again. And I'll probably go. They were in Sacramento. They will be in Sacramento next month, so probably I'll be there. And this is my family in Italy. I got to visit them. Hopefully, I'll visit them very soon. I had a baby in 2017. This is her. And then April 2020, I have a second one, and my husband in the meantime also got very good at making pizza. So now we have pizza that is competitive with the best pizzas you find here, but also in Italy. So anyway, this is about me. I hope you enjoyed it. Okay, so now more into the science part. My talk is about designing and characterizing integrated system for solar fuel production. I believe all of us in this room are motivated by trying to fight the climate change and try to find a solution to the energy problem. We know we have rising levels of carbon dioxide that generates an increase in the global temperature. Arctic ice decrease and ice sheet decrease that generates sea level increase. I really like to talk about how the United Nations look at this problem. So they developed 17 sustainable development goals. Probably the most relevant to my research is goal number 7, affordable and clean energy. So these are all their goals that goes from no poverty to partnership of the goal. And all that is there in between is just a box in itself, but actually all the goals are connected, because if we can make renewable energy sources that are low cost, that can help everybody on the globe, that would actually really bring us, in my opinion, to a better future. How do they advise us to do this? By collaboration. And again, I'm really keen on collaboration, but because I think that working together can lead us to bring a solution faster. So again, maybe this is, you already know this. There are people that think that climate change is not a problem because maybe you see that some parts of the world are really hot and some parts are really cold. So you don't get how the temperature overall is increasing, but it is increasing. So this is how the temperature has increased over the years, and you see that the globe overall has become hotter and hotter. And the fact that we observe these extreme events, either very hot or very cold, is just a consequence of this temperature increase. And this is the annual temperature anomalies over the years. So what is the solution to all of this? Again, I am not here to promote what I do, but I'm here to try to get people interested in climate change and finding a solution. So there are several solutions out there, and in my opinion, there is not one that is right or wrong, and probably all these solutions will have to work together where it makes sense regionally to give us our future. So we have solar cells, we have wind. Just this month, the Department of Energy has a new Earthshot goal on offshore wind. I think it's going to be very important in the US and in Europe as well, where there is a lot of opportunity for offshore wind. Batteries, I was talking to Alyssa before about batteries. They will be part of a solution, but they will not be the solution, in my opinion. And I have a couple of slides on this as well. And then there is a huge effort in decarbonizing the chemical industry. Chemical industry actually takes a lot of energy, and probably even more than the energy that we consume with cars or with airplanes, because we produce chemicals, everything just runs around the chemical industry. So finding ways in which we can make chemicals by electrification is going to be really important in the future. So I just focus on comparison between batteries and making chemicals by electricity, either by utilizing sunlight or just by electrocatalytically. And what's interesting when you look at making chemicals by electricity is that the cost of energy now, of power, has decreased a lot over the years. And we are perfectly on track to meet the government's goals by 2030 in reducing the cost of energy. Another thing that we should consider is that solar and chemical fuels are a convenient way to store electricity, as their volumetric and gravimetric energy density outperform batteries. And I show this here. You have lithium-ion batteries here. This is the volumetric density, and this is the specific energy density that you can also look as gravimetric energy density. And if you look, for example, where fuels are, hydrogen is here, and other fuels that we can make by electrochemical or photoelectrochemical reduction of carbon dioxide are up here. So both hydrogen and liquid fuels are potentially a better solution than batteries currently. Maybe the battery industry will come up with something better. So I mentioned that I have worked for 6 years for the Joint Center for Artificial Photosynthesis. And it's a collaboration between Berkeley Labs, Caltech, UC Irvine, UC Davis, and SLAC. First 5 years were focused on the integrated hydrogen generator. And it's correct. I worked for Jacob for 6 years. And then second was focused on CO2 reduction. So that's how I got in CO2 reduction. And now I'm working for the Liquid Satellite Alliance. In addition to UC Irvine, UC San Diego, Caltech, and SLAC, we now have NRL. NRL is very well known for photovoltaics. There was a strategic partnership that we got there, and we also have University of Oregon that joined the team. The focus of LISA is really looking at microenvironments and catalytic microenvironments, and understand how you can engineer and how you can co-design the microenvironment to make the products, the CO2 products that you want. And I will tell you more in details what are the challenges of CO2 reduction. So you'll see that, and this will make more sense later. Before going into the details of my research, I want to tell you a little bit more about the philosophy around my research. I like to adapt a quote from Peter Drucker. If I can understand, I can improve it. He was saying, if I can measure, I can improve it. And so a lot of the research groups, including mine in the past, were focused on efficiency. And still now, there are a lot of people that are doing that. However, efficiency is not the only key, especially if we want to have a more sustainable future. And we really need to start looking at durability of system, or repairability and recyclability. And so how do we do that? We need to understand how a system works and why they fail. And my approach to do this is to start from synthesis of materials, utilizing operando and in situ characterization techniques. I do both the chemical and morphological and functional type of characterization. I take the information that I learn and I feed them into synthesis to try to make better materials that are more durable. I'm at the stage where the materials are more durable. I'm not yet at the stage where they are repairable or recyclable, but I want to get there. So I applied this philosophy to integrated solar fuel generators. Solar fuel generators have very different components. They have catalysts that are interfaced with the electrolytes. They have light absorbers. You see here photoanode and photocathode that are interfaced with the catalyst. And they have layers that allow for charges to move across the device to perform the chemical reactions at the surface of the solar fuel generator. At Elgano, I look at different facets of the solar fuel generator. As I said, I look at interface engineering. We do direct engineering, direct interface discovery of materials combination that can bring to high performance and high stability. I look at transformations of these solar fuel generators over time. I try to make materials that are selective for the chemical transformations that we want to study. And I try to do all of this with sunlight. So it's an adjunct challenge, but we can utilize sunlight to produce those charges and to get the chemical products that we want. So today I'm going to talk to you more about how I characterize these systems. And I'm going to talk to you about more how we look at local environments and we engineer local environments for these chemical transformations. So here a little bit of fundamentals about artificial photosynthesis. Is anybody really working in artificial photosynthesis? No? Okay. So ask any question that you may have. Basically, artificial photosynthesis takes inspiration from natural photosynthesis, right? So sunlight, water, carbon dioxide are all absorbed from plants in leaves. Specialized bacteria can do that as well. And then you obtain sugar in plants and oxygen, which is a byproduct. So it's a very green process at the end of the day. We try to do that, let's say artificially, like a man-made process that works the same. We do that by utilizing semiconductor materials. So again, just think about taking a solar cell. It's a very similar concept. In this case, we have a junction. We have an N-type material and a P-type material that are put together. And the reason why you want to have a junction is because you need one side of your device to catalyze water oxidation and the other side to catalyze water reduction. So when you have an N-type material and you put it in an electrode and you shine light, you will have bending at the interface. And this bending allows holes, specifically for an N-type material, to go at the surface, and the holes to be utilized to oxidize water. Similarly, at a photocathode material, you have downward bending, and you have electrons that are going to the surface. Now you can utilize those electrons to reduce the material, to reduce a chemical. And so now you reduce water to hydrogen, or you reduce carbon dioxide to other chemicals. The energy that it's involved in this, specifically for water oxidation, is thermodynamically 1.23 volts. But then you have the kinetics that are related to the semi-reduction and the semi-oxidation reactions. And this takes the energy that you need for the process at about 1.7 volts. It means that you need 1.7 volts to autonomously split water. You either get it by plugging the wall, or by having the right choice of materials, shining light on them, and getting that energy, just like with the sun. So here I'm just highlighting that that right choice of material should have at least one of them at around over 1 volt, and the other one is around 0.6 volt, and I'm not choosing this 0.6 volt by chance, but it's silicon. So if you shine light on silicon, you get at least 0.6 volts usually. So we can start from silicon and then try to find a material that can match silicon, and then we can split water on top. This material can be bismuth vanillate. So this is not another, it was a thought choice. Bismuth vanillate can give you more than 1 volt. And you can use this material to oxidize water. It has a band gap of 2.4, 2.5 eV. The band gap tells you about the wavelength that the material absorbs. And as a suitable valence band for water oxidation, remember the upward band bending that I showed you earlier. And when I started studying this material, since it's a metal oxide, it was known to be stable in oxidation conditions. Saying known to be stable because I actually will show you that it's not stable if you want to make a system that can work for several years out of it. But again, because of the first and foremost focus is on efficiency, I also started down that route, and I'm like, I'm going to make BBO better. And making BBO better for us meant doping bismuth vanillate. I'm calling it BBO, but it's bismuth vanillate. We doped it with molybdenum. This is the representation of a sputtering system. I made a 10 by 10 centimeter square slice of BBO just to show that the synthesis was reproducible on a large scale. This is how it appears at the nanoscale by scanning electroscopy. So it's a polycrystalline granular material. You make electrodes. This is a lump scale type of electrodes that I will make. It's 1 centimeter by 0.5 centimeter, roughly. And this is the photoelectrochemical cell that I usually use to test materials. So as you see, the sunlight, the stimulated sunlight is coming this way. This is the electrode that you see here. It's in the electrolyte. Then you have a counter electrode, this blue one, and the reference electrode, the silver chloride one. And then you're working, which is this one, is here in the middle. And then you measure CV, current voltammograms. You look at the performance of the material. So if you don't have any doping, you have kind of a very sad and flat curve. But then if you dope the material with molybdenum, then you see a shift in the onset potential. And this is really important because it tells you the operating voltage of the material. And then you see also an increase in the current density, which is also another factor that tells you that the material is performing well. So we show that we can make this material scalable and reproducible. We show that we could improve the performance of the material. And then the next step for us to demonstrate that we could actually make a working device was to show that the material had a stability of at least 100 hours. And this is when I became very sad. Because ideally, and this is normalized photo, kind of just for simplicity, but ideally what we would like to have is like that your material is just really stable and stays at 1. But then this is a near neutral pH, so very gentle conditions if you want. But already after 1 hour, the photocurrent is almost done. pH 12.3, which is a usually good pH to perform water oxidation. Situation is even worse. After 10-20 minutes, the material is completely done. And so for for me at the time and for my research group was a lot about understanding why this material that was reported to be stable in literature, because probably people were just testing it for 1 or 2 minutes that were getting like the efficiency parameter, was instead not stable. So the very first thing that we did was just looking by scanning electron microscopy at how the material was changing over time. So this was an ex situ analysis that we did. Here, because of the lighting, you cannot see it very well, but you saw images earlier. The material is polycrystalline, is granular, but those grains are well defined. And then when you put it in a solution, those grains are not well defined anymore, and they start fusing together. After fusing together, they actually leave the substrate, and this is at 20 minutes at pH 12.3. So the chemical analysis can also provide you more information about the degradation process. And this is what we did. We took the electrolyte that was in the photoelectrochemical cell and we analyzed the contents of atoms of ions that were in the cell. So we looked specifically at vanadium and bismuth that are components of bismuth vanadium. And we looked at the content in the electrolyte to find out a few things here. This was done by ICP MS, inductive photoconductive plasma mass spectrometry. So the degradation depends on light. Shine light on the sample, it will degrade faster. On increasing pH values, that was obvious from the SEM images that I showed you earlier. On applied bias, the higher the bias, the operating voltage of the device, the faster the degradation. And also the concentration of the electrolyte, which I haven't told you, but it's actually an important parameter to ensure conductivity of a solution. You want the electrolyte to be highly concentrated, but the high concentration is actually damaging the material. In order to understand better corrosion, you can use computational approaches to this. And so here I mentioned about the conductance and valence band earlier, and upward band bending. So just focusing a little bit more on the ideal process, you shine light and you have charge generation and separation. And ideally, what you have is that the holes that are going at the surface are oxidizing water. However, they can also oxidize the material. And understanding the equilibrium between the two processes becomes really very important. How is it done? A colleague of mine, Lin-Wen Wang, and he's now retired at Lawrenceburg National Lab, published this very interesting library of compounds in which you see conductance bands, valence bands, and in red, the oxidation potential for water in the dashed line, and in the solid line, the self-oxidation potential of the material. And for simplicity now, I would just ask you to ignore this upper part and just focus on the lower part of this diagram. So if you look at bismuth vanadium, you see that the oxidation potential of the material is actually very close to the self-oxidation potential of the material itself. So the equilibrium between for the holes to decide to go either to oxidize water or to self-oxidize the material is very small. Like holes may decide to go either way because the two oxidation potentials are very close. However, if you look at a material that is known to be very stable, hematite, you know what's another name for hematite? I cannot hear, sorry. Rust, right? Do you know anything more stable than rust? So you look at the potential, the oxidation potential for water, and you look at the self-oxidation potential of hematite, they are also very close. So that cannot self-oxidize as well, but it doesn't. So it means that thermodynamics in this case is not enough to just explain why a material can oxidize. And there needs to be more consideration, specifically kinetic type of consideration, to understand what's going on during to a material during operation. So we collaborated with the Materials Project, which is an open source database that you can find online. And they are able to make Purve diagrams, which are basically phase diagrams in which you can understand whether material is stable with respect to the applied potential and to the operation, the pH of operation. And for this modality, you see here, the window of stability is actually very small. And up here, it's the oxidation potential of water. And you see that at operation, actually, this modality is never stable. So what should happen to the material, though, is that you should have a bismuth oxide layer that is solid, that should form on top of the material. But this is not what we were observing. We were observing something different, that the material was transforming and eventually leaving the substrate. So we told this to the materials project people, and we told them, look, your bismuth oxide is actually not forming. I'm not sure what's going on here, but there is something different going on. So they were able to prevent the formation of that bismuth oxide phase and to let the system relax basically and see what other phases could form under the same conditions. And they came up with this bismuth oxide hydroxide ion that is soluble and can go into solution. So we try to do more than to understand this prediction and to understand how the material was developing and transforming over time. We did this by electrochemical atomic force microscopy. So it's a microscopy that allows you to look at materials with a very high resolution, and the resolution depends on the tip that you're using. So you can go down to the atom level, really. But in this case, if you're not in high vacuum condition, usually you get between 10 and 20 nanometers of resolution. And because I was using this electrochemically, then we can observe transformations as they happen as we apply potential. And you can use also this technique to look at functionality. If you shine light on the sample, you can also collect current from the sample. And you can get maps of photocurrent on the sample. So this is how the system works. As I told you, this is the tip of the atomic force microscopy. It's on a cantilever. And you scan it on top of a sample, a light absorbent in this case, which is also your working electron in the electrochemical cell. And then you have a counter electron in your reference electron. And then you can collect the videos of your sample, and you can understand how the material is degraded. So you can focus on anywhere on this video, but what you'll see is that the material is etching away. And with this technique, we were able to look at the real-time transformation of the material. And we were able, with statistical analysis, to understand that the corrosion process starts at the solid-liquid interface. So whenever the material is exposed to the liquid there, it's where the degradation is going on, and then it just propagates to the rest of the material. And this is very much in line with the information that I showed you at the beginning, to scanning the electron microscopy. So you can look at all of this morphologically, but then it's also interesting to understand what's special at those interfaces and what's happening from a nanoscale perspective, from the functional point of view. So how the material is functioning at the nanoscale. And we did this with photoconductive atomic force microscopy. So you shine a laser, you back illuminate a sample, and you're now using your conductor, your probe, your atomic force microscopy probe to collect the morphology and current from the sample. You can collect current maps, and the different contrast that you see in these maps is actually a different photocurrent that you're measuring. And you can also collect IV curves. So think in terms of the cyclical thermogram that I showed you earlier. You have an IV curve, we just understand more about that specific region. So now we are measuring at 10 nanometers, basically, what's happening and what current we are collecting from that region. And we can basically understand more about charge transport at a nanoscale. For clarity, for the physicists in the audience, we are of course course, measuring this properties for the whole system. It's not for the DBO only. And so there might be changes in case you change the substrate, for example, or you change the tip with which you're measuring. But in general, this is what you get. You can have a topography, and then you just see how the materials appear, and then you have the dark current and the photocurrent, and depending on the wavelength that you're using, you can excite the material above the band gap or below the band gap. And depending on the excitation, you can get information about defects in the material. However, and again, I'm not sure if anybody is working on atomic force microscopy, but if you do, you might know that it's a technique that is very prone to artifacts. And you can actually get very sidetracked when you look at your data if you're not careful. So something that we did here was trying to find if there were correlations between the data that we were measuring and the photocurrent that we were measuring. We didn't want any correlation because in that way we knew that that there were no artifacts. So once we did that, we started with the statistical analysis. And with statistical analysis, you have the topography here, you have the maps of the photocurrent, and you have the control, which is basically when you're not shining light. Then you can understand what is generating the most of the photocurrent in your sample. So here, the first piece of knowledge that we learned is that optical excitation above the band gap is the one that gives you the photoresponse, which means that the defects in the material are not contributing too much to the photocurrent. And then you can focus in smaller region of the samples and you can try to understand where the photocurrent is coming from. And we identified three different regions: the grain boundaries, the facet plane, the facet boundaries, and we found that the higher photocurrent was coming from the facet boundaries. Instead, by looking at the IV curves, we were able to determine relationships between the current and the voltage, and by these relationships, we were able to find out that there is a power law dependence between current and voltage, and this power law dependence is in line with the space charge limited transport in the material, which basically tells you that the material is limited by the majority carriers. I talked earlier about holes. Majority carriers for DBO would be electrons. So it means that the holes are perfectly fine to go to the surface, but actually the combination with electrons can kill the material. And it literally does, right? We've seen that. So yeah, here just to summarize about the photoconductive microscopy, we were able to find the charge transfer mechanism at the nanoscale and to provide one more piece of information on why the material is degrading. So I told you about morphology, I told you about functionality. However, there is another important part in all of this, which is chemistry. And possibly chemical mapping of elements in the material to tell you more about the degradation. So we utilize scanning transmission X-ray microscopy, and scanning transmission X-ray microscopy is a technique that is available at the Advanced Light Source. It allows you to take an X-ray absorption spectrum at a spot with a spatial resolution that is 20 nanometers. And in this case, we're looking at the vanadium and the oxygen edge of the bismuth vanillate, and then we can understand how these X-ray absorption change over time when we test the material. Basically, this is the schematic of the beamline at the ALS and where we perform the measurements. So here you see the AFM morphology of the S-grown bismuth vanillate and the one degraded over time, and then these are the energy filter images that we collected at the scanning transmission X-ray microscopy beamline. And again, you can find the different areas. You can find the grain boundaries here. and the grain centers. And we focus on these two areas to understand the differences in X-ray absorption spectrum. We found basically two components that were also confirmed by principal component analysis. And these two components are indeed related to the grain center and the grain edges. And of course, we started biased because we knew that there was something going on at the electrolyte electrode interface. But by doing the principal component analysis, we basically took away our bias and we asked the algorithm to calculate for us what the different components in the spectra were. And by principal component analysis, we did find indeed that these two components are related to grain centers and grain edges. And what's special about this is that at the grain edges, and you see it, I'm saying you see it from here. Now, because of your background, I'm not sure you can really see it. And of course, there were calculations that were made and a lot of analysis that went into this. So believe me a little bit here. But what you can extract from this spectra is that at grain boundaries, you have a phase segregation of vanadium oxide. And this phase segregation of vanadium oxide is the one that can lead to the corrosion. Vanadium oxide is more soluble. And by being more soluble and by phase segregating at grain boundaries, then it can leave the material and basically generate that corrosion that I showed you earlier. So by utilizing all these techniques, we kind of completed the picture on the gradation of this quantity. Still not able to make it exactly stable, but it's still one of the goals that I have. But what we did by learning, by the learning that we gained on that material was to adapt this learning on another material based on silicon this time. So we're looking at the photocathode side. And by working with a collaborator at the University of Michigan, Professor Zedley, he deposited gallium nitride on top of silicon, and he knew already that the system somewhat was stable, but he didn't know why. So we did more analysis, the type of analysis that I just showed you, on the silicon gallium nitride system, and we found immediately something very interesting. So I showed you earlier the cyclical thermograms of PVO. Now you see this reverted because we are on the cathode side. But the principle is the same. You are looking for the onset potential of this curve and the photocurrent density. And in this case, you want like the more anodic the shift is, the better. And of course, the higher, but in this case, it's in negative values, the better. So we tested the material and at time 0, and then we started running chronometers, which is our way to look at stability of material over time. And then we took cyclical thermograms or linear cyclical thermograms in this case every so often to just try to understand if the material was changing, and it was. And surprisingly, it was improving, which is kind of unexpected. And so we try to understand why the material was improving. So we did the X-ray photoelectron spectroscopy, and in this case, you're looking at oxygen 1s. You just look basically at the composition and the oxidation state of the different elements in the material. But here you're just mostly looking at oxygen. And this is the oxygen 1s of the pristine material. You have the oxygen bound to the gallium, so this is just by absorption. Because you have gallium nitride, you shouldn't have oxygen, right? But then because you're exposing your sample to air, there can be water that absorbs, there can be oxygen that absorbs, and that's why you see it. And in fact, we see the oxygen bound to gallium, but also the hydroxyl groups because of water absorption. Then we start running our measurement, and what you see is that there is a new peak. And in literature, we found that this new peak that was forming was probably related to oxygen nitrogen. So oxygen bound to nitrogen of gallium. And this component kept increasing over time, and we reached a kind of a maximum at about 4 hours. So we did again a photoconductive atomic force microscopy to understand the current distribution of the material. What we observe in this case is that the photocurrent distribution was actually quite homogeneous all over the material. But what changed surprisingly is that the pristine material has about 3 orders of magnitude less photocurrent than the tested material. And what we observe is that we have very high spikes of photocurrent, again, grain boundaries. Again, the grain boundaries were a place where something was happening. We utilized the scanning transmission electron microscopy, this time with a molecular foundry, that basically allows you to look at the material. So this is the gallium nitride layer. And we can look at the nitrogen, the gallium, and the oxygen edges to try to understand the chemical distribution. So in this case, on the side wall, you have nitrogen localized with gallium, and then oxygen is just not present. And then on the top of the material, you have nitrogen. You don't see nitrogen, but you have a layer of gallium that is oxidized because oxygen is bound to it, and that corresponds also to the XPS that I showed you earlier. Once we run our tests, what we observe is that still on the top surface, you don't have nitrogen, but you still have this component of gallium bound to oxygen. And then the side wall, here is what something interesting is happening. You see nitrogen, you see gallium, you see oxygen. So you remember that XPS spectrum that I showed you earlier? This is the peak that we were observing, and it's related to the side wall. And it's also confirmed by the photoactive atomic force analysis that I showed you earlier, where you see that the higher photocurrent is coming from the side walls. So the second part of the talk, I might be a little bit slow here, but it's about nano-interfaces and the design of microenvironments. I can stop at any time, I guess. Okay. Okay, sure. Okay, so I mentioned earlier about the challenges of CO2 reduction. CO2 reduction is challenging for many different ways, but the first and foremost reason why this is challenging is because you can reduce CO2 to almost anything. And it's an issue if you start thinking about separation of the products and how you become efficient in a reaction. So you see here, depending on the amount of electrons that are involved in the reaction. And of course, you want the highest number of electrons because these molecules are more energy dense than just carbon monoxide. But because you have so many electrons involved, then the reaction becomes really unselective. And there is an opportunity there to control the selectivity instead. So I told you that we draw a lot of inspiration from natural photosynthesis. And in natural photosynthesis, you take carbon dioxide and you make glucose. And the enzymes that does that is the Rubisco, and has a catalytic site that is very well designed to do this reaction selectively. So in the catalytic pocket, there is not only the catalyst, but there are also all the amino acids that are providing that specific microenvironments where the enzymes can work so selectively. So how do we do that from, let's say, an artificial process? We looked at different catalysts or different elements, catalytic elements that are out there. And what you can find is that there is only one element that can really go beyond CO, which is copper. And then there are other elements that can make hydrogen preferentially, or CO preferentially, or formic acid. We can vary the catalyst morphology, and varying the catalyst morphology can actually lead you to be more selective. We can look at different pHs. Higher pHs are reported to give more C2+ products, or the electrolyte choice. If you change the cation of your electrode from the electrode that you use usually in CO2 reduction is carbonate, because you want a buffer, you have a CO2, You put it in bicarbonate and you get a buffer, basically. And the pH doesn't change, but you can change the cation of that carbonate buffer that you make. And if you do cesium carbonate leads to more, to higher hydrocarbons. And then, of course, the applied potential. I showed you earlier, you have this multi-electron process. The more potential you apply, the more electrons you can get. So we took copper because of the above reasons that can give you products beyond CO easily or more easily than others. And then we wanted to make copper selective. So we changed the morphology. I told you it has an effect on the selectivity. And then we functionalized it with different molecules to understand how the local environment, very similar to the catalyst, can affect selectivity. So here are different molecules that we utilize, so polyvinyl pyrrolidone, and then ammonium salts, and then amines derivatives to understand the selectivity. And what you found is that when you use protic species, like in this case, you can have an increased HER activity. So the blue here is hydrogen. And then a protic species instead gives you more selectivity for formic acid, like the polyvinyl pyrrolidone case. And a case aside was represented by the ammonium salt that were having different behaviors with respect to the substituents. So here you can see more in details about the different roles of the substituents. And you have different, you have alkyl chains with different lengths that are substituting this ammonium salt. By looking at the different lengths of the alkyl chains, you can see how you can become more selective for CO, more selective for formic acid. And so we basically found a correlation between hydrophilicity and hydrophobicity and CO production. And you can see it summarized here. If you measure the contact angle of each functionalized surface that we made, and you compare it with the product distribution between formic acid and CO, you will find that more hydrophilic surface will give you more formic acid, and more hydrophobic surfaces will give you more CO. What this is telling you is that, of course, water has a role in the reaction, and the amount of water specifically that is present on the catalytic site has a role in the reaction. We studied this by molecular dynamics in collaboration with the brothers at Caltech, and this is basically the simulation of our substituents. You can see them here embedded into water molecules, and you can basically quantify how much water is here at the surface. And you see how much water, like the water densities at the surface as a function of the distance from the actual surface. You see here that the hydrophilic substituents has more water than the hydrophobic substituents. But then if you actually calculate the energy for the production of formic acid or CO, you find that the hydrophobic surface, which is the one here, has higher energy for formic production, which explains why you get more CO. And this is in line with the mechanism that gives you CO versus formic acid. We looked at water. Another thing that we looked at is CO2. And we did that by looking at silver. I told you that silver gives only CO basically, and so this is a much simpler example. We still looked at substituted ammonium salts, and what we found was that so this is the class of the ammonium salts that we use with one C16 alkyl chain, two C10 and one C10, and you can see that when you have two C16 chains, you basically become selective for carbon monoxide. Sorry, this is gray hydrogen, and this is just unfunctionalized silver. You see that you go from 80% selectivity for hydrogen to almost 99. This in this case, the total Faraday efficiency was 97 Faraday efficiency for CO. So we were able to take silver and make it really selective and low over potential for CO. Why? Because of the concentration of CO2 molecules at the surface. So all these difference of sequence actually are able to concentrate the CO2 locally in a different way. And the 216 derivative is able to actually give you much more CO2 molecules at the surface than, let's say, the C10 or the 1C10. And this tells you why you have more CO, because you actually have more availability of CO2 at the surface that can convert. The microenvironments is also important from the electrolyte perspective. This is now a different material. It's a material that I worked a lot on the past 5 years, fused oxide. Very earth abundant material, but unfortunately also very unstable. It's reported for hydrogen production. My group for the first time reported fused oxide for CO2 reduction. So we studied the stability of this material in different environment to find out with operando X-ray photoelectron microscopy that the material transforms in different ways with respect to the electrolyte which is in. So it's extremely interesting because you don't change anything about the pH or the applied potential, but you just change the cations that you have and the anions that you have in your solution. And it changes everything on the material stability perspective. And I get that there are people here from civil engineering and another field, and so it might be very obvious in other parts of science, but for us, that we just make materials and try to characterize them. All these things are not so obvious. So that's why we also need to figure them out. And so in this case, we found that there is a component of hydroxide ions that can attack the fused oxide, especially when you are in bicarbonate, which is the electrolyte of election for CO2 reduction. So in summary, I showed you how, like a general approach to characterize solid fuel integrated system. I showed you how we engineer microenvironments, and we try to understand the structure activity relationship in solar integrated solar fuels. And again, I want to come back to my original quote from Peter Drucker. We do need to work on durability now more than ever, and try to shy away from efficiency, or at least find an equilibrium between the two. And I just want to put it out there. I know that this is probably one of the goals of your program, but in the future, and this is by 2050, the International Agency for Renewable Energy says that we'll have 70 million tons of waste that is due to the photovoltaics industry. So now that we're working on renewable energies, I think it's really important for us to start thinking about recyclability. And I discussed quite a bit with Professor Kendall before this talk about repairability of the systems. This is, in my opinion, where we should focus in the future, trying to make systems that are recyclable and repairable from the start, and not just focus on the future. I want to thank people in my group. Ian Sharp, Chisholm Cooper contributed a lot to the first part of the Bismuth Vanillate project. Zetya Me for the gallium nitride, and Luke Dost for the microenvironments. And the students that did a lot of the research represented today, Joanna Hayford, Luigi Lee Wilsons, and Aya Buckley. And of course, funding. It's always important to let us do research.
Hey there. So I read your paper on Cooper's oxide and PEC development, and degradation seemed to be the biggest challenge for that. In terms of abundant PECs, do you think there's a scalable option in the future? Do you think Cooper's oxide is worth, kind of continuing to pursue, or do you think there's a better alternative out there?
No, there is no better alternative out there, which is sad, but maybe there will be. We are working on there was a paper from 2019 from the person group on inertial communication. If you're interested, I can send it to you. They basically try to put some constraints to the materials and try to predict the material that is stable under CO2 reduction conditions. Zinc telluride is one of them. We're not working on zinc telluride. We're still figuring some stuff out, so I didn't present it today, but that might be interesting material. The issues with all of these materials are related to how much photovoltaic you can get out of them. And it's extremely important for CO2 reduction and together with current density, because it's shown that there are limitations with respect to the onset potential, to the photovoltaic that you can get, and the current density, operating current density. So I think that our study showed that you can make selectively ethylene, and it's the first one that reports that. I don't know of any other better alternative. We were able to make it stable for 24 hours. And I know that it's nothing that you can go to the industry and say, hey, use my material now. Like they would laugh in my face, I guess. But I think there is opportunity there. Because figuring out how the material really degrades, let us understand how we can fix it.
Hi, I have similar background as well, so I have two questions. So the first part is, you might like explain a little more about how you engineer the microenvironment for the part a little bit more, and also you mind to explain a little more. Do you use the organic framework in the CO reduction or not, or they are only like the organic part is only a substrate for that?
Okay, I'll tell you a secret. It's all serendipity, right? So I'm telling you that I'm engineering things. So the first thing that we do is just try out stuff with a lot. And then we figure out the principles of how we engineer something. So the rationale there was trying to get different functionalities. And then we tried to put them down on the surface. And once we started finding information that was like leading us one way or another, then we would find the choice of those molecules. But the very first thing that we did was just like looking in literature, trying to see what others have done, and just go from there for the first like rough choice of modifiers that we use. Then you asked the question, does it respond to your?
No, I mean specifically because I saw on the research part it says like the granular boundary palladium. What was that? The palladium by oxide.
Oh, okay. So this is related to the first part.
Yeah.
Sorry. Here.
Yeah. So I saw that one that the grain boundary can help to improve the efficiency of this material. So I'm kind of wondering like how that's specifically related, how could that apply to the microenvironment engineering?
Okay, I get it. So in this case specifically, we didn't see that the grain boundaries were particularly high in photocurrent. So in this case, what I would do, I would try to make a material that does not phase segregate in the first place, and try to see if that helps with corrosion. There was a study from Professor Choi. She's a University of Madison, Wisconsin, and she did use a strategy to try to make. Oh yes, and now I remember what she did. She looked at facets. So the crystal orientation is actually very important as well. And this is something that I didn't study myself, but it's in principle very similar to what we are discussing. Like if I can make a specific facet of a material with a specific chemical composition of the facet, then I can study how that holds stability. So that's how the microenvironment can come to place. All of these materials will, I don't have any crystal structure here, but you can imagine that I'm showing you, or maybe let me do this. No. Okay. So of course, crystal solidity will have a crystal structure, right? And then you can imagine a crystal lattice. The termination of the lattice at the surface can be either bismuth or vanadium or oxygen. And depending on what you have as a termination, that can dictate stability. And this was recently started by Professor Choi.
Okay, thank you.
I think, yeah, first.
So with this mandate, degradation seems inevitable, but do you think we increase the longevity of the material by figuring out a three-way axis as to when the photocurrent production peaks and the time on the other and degradation on the other, and then stopping the photoelectric reaction, isolating the material, then starting it again? Do you think is that some way you can increase the longevity of the material, or does it degrade regardless?
Okay, repeat again.
So if you could isolate the bismuth mandate photoelectrode from the entire reaction, from sun, from light, from water, from the electrolyte, and isolate it right when the current production peaks, and then start it again, is that one way you could, extend the longevity of the material? So within that window of stability graph you showed, if you could find a point where the current production peaks and you stop the photoelectric reaction, and would that extend the longevity of the material, or does it degrade regardless of when you start or stop the reaction?
My brain is just thinking, okay, how do you do that? But let's say that you can do that. It's not clear to me how you can do it right now, but let's say that you can do it. The answer is yes, you can stop it, because the degradation is depending on the fact that you're using holes. And those holes.
Exactly. So isolating that extend the longevity of the material somehow?
Right. The way we address this usually is that you align the energy levels of the materials that are in the device in a way that you're more efficient with start holes. So something that I've not shown today, but something that we've done was engineering the surface and do discovery of novel interfaces on how you can become more effective at separating the charges and then keeping them from combining.
The slide that you showed was compared the IDL and the rust.
Yeah.
So I know like there's a long duration battery company called Form Energy, and they basically use like a rusting process. It's iron air rust to, I think they rust the cathode to charge it, and then it de-rust to like discharge it. Might be flipping those, but when looking like at this comparison and your comment about efficiency versus durability, and then also like availability of the material itself, and like iron's everywhere, like it's the most abundant thing, which is why they chose to use that material for the battery. What about iron, or why wouldn't you use it for this? Is it not the right thing? Like, why wouldn't you use that material if you're thinking about, if you're trying to maximize the durability and availability of the resource? Like, yeah, it's like less efficient, but I guess it doesn't like, you don't cross over when it oxidizes at the same time. So it's like, okay, you get around that. Yeah, it's less efficient, but just do more of it, right? Because we have more of it.
Yeah, I think it's very inefficient to the point that I would say it doesn't make sense to use it, but let me explain. Like this efficiency target that we have, it's something limited if you want, because there is no way that you can propose something to work if if it doesn't hit a threshold of efficiency. And let's say that hematite doesn't hit the threshold. There has been a lot of study done on the material itself to make it better, but none of them has really succeeded to make it really better, to make sense to adopt it. The photovoltage that it gets is very low, and the photocurrent that you get is very low. So, like, you're fitting already on two main parameters that are used for material screening. Then yes, the durability is very high.
Right. And then kind of follow up, like this, my background is not in this at all. So I'm connecting to the things that like are similar in my mind, and one of that is just like batteries, right? It's similar. There's a cathode anode, there's a reaction, and then usually it's charged for this or producing product. Have you? Is there any correlation between, like, or have you seen correlation with like, a material that's used in a battery that can be used for this? Like, is there crossover and cross-pollination of the battery chemistries into something like this?
Yes, it's a area that I don't know much about, and I always promise myself to read more. Redox flow batteries
Okay.
are very similar to this process.
Right. Okay.
I wouldn't be able to tell you like how one can contribute to that field, but it's very similar to this process. Yeah. You had another question?
Yeah, I just have one about, can you help kind of clarify the relationship? So with grain boundary degradation, that was shown to have a relationship to hydroxide concentration. So if you run in a really basic space, do you get high efficiency, but it degrades really quickly?
Yeah.
Okay, and is there any material that you found degrades less quickly and has some other grain boundary relationship?
In alkaline environment?
Yeah, in an alkaline. Compared to cuprous oxide, for example.
It's not an alkaline environment, but let's say same pH, same conditions and everything, zinc are very stable. And even at a high voltages. We find a correlation between light and the type of products that we get, which is also interesting. But we haven't tried high pH to see if it's like what's the salinity in that case. It's a good point.
Oh, sorry, were you gonna?
Maybe the last one.
Okay. I just had a very general question about the whole materials recycling process. Do these catalysts, I guess, degrade the material in a way where they can't be used for catalysts like this in the future?
There are ways that you can do it. So, for example, you can strip the catalyst from an electrode just by electrochemistry. You deposit it on another electrode and you can take it out. And then I'm also trying to utilize organic semiconductors. They offer more opportunities for recyclability. You can burn them. Maybe it's not environmentally friendly, but if you pyrolyze them, you can make hydrogen. You can electrodes like porous carbon that you can reuse for catalysis. So those are at least ways where you can start thinking creatively that way. I know it's by any means it's an optimal solution, but it's something that can lead us in that thinking.
Interesting, thank you.